Jamie. I'm going to talk about categorical properties of the complex numbers. Right. So, what's the basic idea? When we do quantum mechanics or quantum theory or something like this, typically we use mathematics as based on the complex numbers. If you're doing quantum field theory, you use functional analysis. If you're doing quantum information, we work with finite dimensional vector spaces over the complex numbers or whatever, but the complex numbers are there. No one really knows why they're there from a physical perspective. It's difficult to give a totally non-mathematical argument for why we use the complex numbers. At some point, we just have to give in and say, well, we've got this sort of mathematics that we've used for sort of 80 years. It does the job. We don't really know why. We don't really know why God chose the complex numbers, but it seems that they're there. So, what I'm trying to do is to find an answer to this question: why do we use the complex numbers? So, one way to sort of approach this is to, especially from the sort of categorical perspective that lots of us are working with here, is to find a way to sort of axiomatically present, say, the category of Hilbert spaces in a way that doesn't mention the complex numbers at all, or even anything sort of remotely similar. So that's the sort of thing that I'm trying to do, right? So that's my introduction. But really, these sort of axioms that I come up with, I really want them to be physical and meaningful. I don't want them to just be some abstruse replacement for you can come up with all sorts of funky, unrecognizable definitions of the complex numbers. I don't want to use something like that. I want something that's physical. Okay, so that's the idea. Right, so I'm going to present it in a slightly different way. Let's say we've got some candidate theory of physics. Okay, so quantum theory would be a sort of theory of physics. You can come up with lots of other sort of exciting theories of physics. And I'm going to say, okay, what does it mean? When does this category somehow contain the complex numbers? What physical properties of this theory imply that this theory somehow is built on or uses the complex numbers? Okay, so here's how we're going to apply this test to our theory of physics. First, we're going to isolate a collection of systems and a collection of processes. Now, there are lots of different ways you could do this. So, for quantum theory, we can take a category of finite dimensional vector spaces, a category of infinite dimensional vector spaces. We could take we can use completely positive maps as our morphism. We can make lots of choices. The idea is here that if, at least for one choice of how to interpret the phrase system and process, we end up with a category that satisfies the property I'm going to describe. And that will tell us that the theory is built on the complex numbers. Okay, so we're going to want some pretty standard things. We want to take our theory of physics and isolate some systems and processes. These are going to form a category in a sort of obvious way. So that's just really that definition of a category I've written down there. So intuitively, we might want to think that our systems are sets of states, and our processes somehow functions that transform states of the codomain system into the states of the domain system, states of the codomain system. But we don't need to know what those sets are necessarily. Okay, so I'm going to describe some structure, which I hope can be sort of interpreted in a sort of physical way, that we're going to require to live on this category. Okay, so first of all, we're going to need a dagger functor. So this is something that I'm sure lots of us have seen before. For every process F that goes from system A to system B, we want a reversed process, which we're going to call this adjoint. We want to satisfy some nice properties. If we reverse a process twice, we can get to where we started. And if we reverse identity processes, nothing happens. And we want that to be compatible with composition of processes. And then we can define some nice words that are familiar to us when working with Hilbert spaces. If some process F followed by its adjoint gives us an identity, then we're going to call F an isometry in a sort of abstract way. If some process F has an inverse, and that inverse is its adjoint, then we'll call it unitary. And if some process goes from a system to itself, and it equals its adjoint, and we'll call it self-adjoint. So these are obvious generalizations of words we're familiar with from standard functional analysis. Okay, a second structure I want on my category of processes is a superposition rule. So if you're a category person, then we'd probably call this enrichment in commutative monoids with all it means is that for any two parallel processes going between the same system, so A to B, we can add them together. There's some third process called F plus G. And this addition operation must have a unit, must be associative, must be commutative. Why? Okay, so that's what I've described there is quite familiar. I'm sure lots of people have seen that sort of thing before. But the importance of new structure that I'm going to describe is something called dagger limits. I'm going to require that this category of processes has something called dagger limits. So dagger limits really are just ways to say, okay, if I've got this little, here's a pattern, if you like, a diagram of systems and processes in my category. You might say, okay, I want to somehow glue, I want a sort of composite system of all these systems, A, B, C, D, E, but I want to quotient by the action of these processes. So if these really were Hilbert spaces, these were all just A, B, C, D, E, were just composed of sets of vectors, then the limits, so if we get the dagger business at the moment, we know what to just think about limits. The limit is just the set of the Cartesian product of all of the set of states of A and of B and of C and of D and of E. But if any two states of any of those objects, say A and D, are related by some process, say H, then we identify those two. So basically, we stick together A, B, C, D, and E, but quotient by the action of the diagrams that we've got there. So that's what a limit normally looks like, an ordinary limit in category theory. And a dagger limit that I'm going to find is going to be a special sort of limit.
For limit not to take a subset instead of one?
Sorry?
Usually when you take a limit, you take a subset of things to satisfy the range of common.
So we're sort of guiding our intuition from the category of Hilbert spaces where everything's sort of limits and colimits end up being sort of the same. But, yeah, that would be a more general way of describing it. Okay, so I'm sure most of us are familiar with what a limit is in a category. So I'm going to let this object L be the limit. Okay. Now, the interesting thing to notice is that there's a sort of canonical map that goes from L to the direct sum of A and B and C and D and E. So that's because of what I was just talking about. We can see this object L as a set of states of A and B and C and D and E, which are somehow invariant under these processes. So this is naturally a subspace of, I've written this as the direct sum, but you might want to think of it as the Cartesian product. To turn out that the Cartesian product is a direct sum, so I'm sort of using notation here. So we're thinking of this limit object L as a sort of physical system that reflects the fact that we're taking all these five physical systems, somehow combining them into one big system, quotienting by the action of these processes. But the category theory tells you that you're doing it this canonical map, which I call phi here, and abstractly this will always be monic, which basically means it just effectively determines a sort of sub-object. L fits inside A plus B plus C plus D plus E. But in quantum theory, whenever you have a subspace, it's interesting to say, okay, I've got, let's say I'm working with Hilbert spaces, all my objects, vector spaces with norms on. I want my embedding to be norm-preserving. I want to preserve probabilities and so on. But we can capture that exactly using our abstract structure. In quantum theory, to say that something is norm-preserving, some embedding is norm-preserving, we would argue it's an isometry, but we have an abstract definition of that. So the abstract definition is just that phi, followed by a phi dagger, it's just the identity on L. And it turns out if we require that, that's exactly the same. Requiring that this phi is an isometry. It's exactly the same as asking that all of these limit maps, LA, LB, LC, LD, LE, are sort of jointly isometries in this way. So if we perform LA and then LA dagger, and we take a superposition of doing that for A, B, C, D, and E, we should get the identity on L. That just says that this time phi is an isometry. But an interesting thing is that, of course, for this diagram that I've drawn, some of the limit maps are redundant. So we forget about LA and we forget about LD. Now, because of the properties of limit maps, we can reconstruct the other ones. LA, for example, will just be LB followed by F. And LD will just, for example, be LC followed by K. So we haven't lost anything by forgetting about a few of those limit maps. So by a similar sort of argument, because L is completely determined by sort of how it embeds into B and C and E, we also have a canonical mnemonic map from L into B plus C plus E. So I've forgotten about A and D. I'm allowed to do this. So we can also say, okay, well, what if this map was an isometry? And ask that, and that will translate to this condition, saying that L somehow fits isometrically into B and C and E stuck together. Now this is a different condition than the condition we had before. If we had LA, LB, LC, LD, and LE satisfying this condition, then they won't satisfy this large condition. So these are different conditions, and we have to decide which one we want to satisfy, and then we can try and find A, B, C, D, and these limit maps that will satisfy them. Okay, so what we're doing in general here, let's call some subset omega of our systems. So we've got A, B, C, D, and E here in our systems. We'll call our subset universal if we can recreate all the limit maps just from the maps to those systems. So that B, C, and E are universal. Obviously, we take all the objects, that would be universal. But we couldn't just take A, B, C, D, for example, because then we'd have no way to recreate LE. So, for example, we can choose omega as B, C, and E. Then what we're going to do is we're going to require that for any possible choice of universal systems omega, then we can choose limit maps which satisfy this isometry condition. So if we have a diagram and we choose some systems, a universal set of systems, then if we have a limit to the diagram, that's a limit. But if we also have a limit satisfying this isometry condition for our chosen set of universal systems, then we say that we have a dagger limit. And so, of course, the dagger limit will depend on which systems we choose to be our universal systems. Right, so that's what it means for a category to have all finite dagger limits. Okay. So the question is, what does this get us if we've got a category with finite dagger limits? So what? Why should we be interested in something like that? Well, there's a few reasons. One of the nicest things is if you consider a discrete diagram. So here's our diagram, which is objects A and B. Then A and B we have no choice of what omega is. Omega must, for this situation, just be A and B. And so we have a limit L with limit maps LA and LB. This is just a product. And our isometry condition in this case just says that. But then it's pretty easy to show that, in fact, this is a dagger byproduct. So we've already talked about byproducts earlier. Byproducts are just sort of nice ways to talk categorically about direct sums. But it turns out that if you have this condition, you in fact get a dagger byproduct, which is a really nice way to talk about sticking systems together isometrically. So it's nice that this comes out abstractly, because this is something that we quite like. And of course, the other neat thing about this is that if you have sort of well-known classical category theoretical fact, is that if you have byproducts, then in a category, then the category must necessarily have a unique way to define this superposition, this way of adding up morphisms. So if we know we have byproducts, then we can then we don't have to worry about specifying which superposition rule we want to use, which enrichment equals to monoids, because there's necessarily a unique one. So that takes away some of the choice. And we also get lots of other great properties that I won't go into, but if you have a category with dagger limits, you can explore its sort of abstract properties and use them to prove things. And the main theorem that I'll present about the complex numbers uses all these sort of, properties. What time did I start? Okay, so far what have we got? We've got our physical theory. We said, okay, from our physical theory, can we come up with some definition of systems and processes from a category? Can we find a well-defined way to reverse processes? I call this dagger functor. Can we find a well-defined way to add processes together? It's the superposition rule. And then if I've got that, can I find a is it possible to talk about gluing systems together modulo the action of processes, which are these dagger limits? So we're just going to require one more thing, which we've already talked about, which is just a monoidal structure. This is something, again, that I'm sure most of you have seen before. It basically says that for any two systems, we can come up with a compound system. So you could think of this as if A and B are physical systems, then A tends to be is having both of these systems somehow space-like separated from each other, going on in different parts of the universe without really talking to each other. We're going to require that this is a unital associative operation, so there must be some trivial system I that's sort of the empty system. So if we take A tends to I with this trivial system, that's just the same as just having the system A. And we must also be able to define some processes in a nice way. Because if we have some way of transforming a process taking system A, system B, some process taking system C into system G, then we should be able to do those processes in a sort of space-like separated way, simultaneously somehow. Okay, so that's just sort of very standard. So altogether, this is what we've got. We want physical theory. We want to be able to take systems and processes from our physical theory, so they form a category, so that there's a dagger function. Dagger limits to glue systems together in a nice way. We have a monoidal structure. So the only extra thing here, this requirement that the unit system, which is this trivial system for this tensor operation, is simple. And what that means is that there's no sort of non-trivial smaller system than this unit system I. It doesn't have any substrate. There's nothing else inside it other than itself. Okay, so what do we get from this? Remember, we're trying to the point of this is to think about the complex numbers and the properties that they sort of give a physical theory. Well, it turns out we don't get the complex numbers, but we get something pretty close. So from this, you can prove that we look at the processes from this unit system to itself. We can think of those as this sort of abstract amplitudes in our theory, so sort of the amplitudes for sort of quantum probabilities and things to happen. And it turns out that from these axioms, you can show that these are in fact valued in a field. So the word field there is the first sort of important, perhaps surprising word. So there I mean a sort of classical mathematical field. You can prove that your amplitudes are, in fact, form a field. This field has an involution, just like the complex numbers, which is a complex conjugation. And of course, the complex numbers have a subfield that is fixed by complex conjugation, which is the real line. And of course, we know that the real line is ordered. And you can prove that abstractly here as well. You can show that the subfield of your processes from I to I is unchanged by your involution necessarily admit a total order. So this is obviously
yeah. Can you say a little bit about what you mean when you say they're valid? Like, do you mean if you consider all the processes from I to I?
So I left that a bit vague. If you consider all the processes from I to I, they will not necessarily be a field, but they will be a semi-ring, in fact, which is a much weaker structure. But you can show that will embed into a field, and not all semi-rings by a long stretch embed into fields. So it is. So you can find some larger. There's some smallest field to which it embeds.
So why can't this field be the real line, for instance? Or can it?
Well, because it just will often. There are lots of ordered fields which do not embed into the real line. Right, so that's the thing that's missing. It's a shame that we can't guarantee that this fixed field be the real line. So at the moment we have an involutive field that's analogous to C in the fixed dimension as. So that's sort of, that's something. We're recovering some of the structure of conventional quantum mechanics. But what about the rest of it? What about really actually ending up with the complex numbers in the real line? Okay, so for this I'm going to introduce just one slide of extra structure that really shows us what's special about the real numbers. So I've already mentioned that our processes from I to I, in fact, just from the abstract properties we have from the semi-ring. So that's just like a ring, so we can multiply elements in a commutative way, we can add elements in a commutative way, these things distribute with each other nicely. But in general we won't have negatives. We'll subtract elements, and we're going to denote all these scalars of this semi-ring by II in square brackets. We'll call these the scalars of our category. So we're interested in these scalars that are self-adjoint, the scalars that equal their own dagger. And these, of course, we've already proved that they admit a total order, and these generalize the real numbers. These sort of are. We would like these to really be the real numbers in our category. So I'm going to write II dagger for the sub-semi-ring of scalars which are in fact self-adjoint. Okay, and this is the property that I'm going to require. For any subset of these self-adjoint scalars, so remember these self-adjoint scalars have a total order. So we can say, okay, this subset, is it bounded in this total order? Now, if it has an upper bound, then we're going to require that in fact it has a least upper bound. Well, in fact, we want this least upper bound to sort of get along with the addition operation on the semi-ring in sort of a natural way. And similarly, if we have a lower bound, then we're going to want a greatest lower bound, which gets along with the addition operation in a nice way. So you can say, oh, what's this this crazy abstract order theory that's now appearing. But in fact, I think these requirements are very physical. Let's say that your theory of physics is somehow going to describe space. Well then, at least in quantum theory, the results of measurements end up being ordered in this sort of abstract, totally ordered semi-ring. So let's say we have a particle moving in one dimension. We want to measure its position. Then the possible values are going to be exactly these self-adjoint scalars. And this is a property, for example, that if you take any set of points in space, this is a property that points in space have. If you have any points along a one-dimensional line, this is a property that they have. So, and again, of course, this is a sort of a completeness property, because this total order, you can think of the total order as a category. So really, what I'm saying here is that if any diagram in this total order seen as a category has any cone, then it must have a limit. Similarly for the co-cones and co-limits. And this property is well known, well studied, and this property is called dedicated completeness. So it turns out this is in fact all we need to add. If we have all our original stuff, and then, like we've already said, that you can prove from this that the self-adjoint scalars in fact admit a total order, an ordered algebraic structure. So we can ask this order to be Dedekind complete. And for that, you can now show that your scalars are in fact valued in the complex numbers, and the dagger functor just exactly takes their complex conjugation. So to the extent that these axioms can be interpreted in a physical way, which I hope that they can, then this goes towards giving a sort of more physical, more intuitive understanding of why the complex numbers seem to crop up, seem to be so useful for quantum theory. And I guess that's it. I guess I'll stop there. Go ahead.
Yeah, so I just have one. I mean, I have a lot of questions, but I'm limited to one. Right here, do you have proof? I mean, does your result imply that you can't totally order the set of complex numbers so that they're Dedekind complete?
Yeah, that's true. So that's quite a classical mathematical result. The complex numbers don't admit any order. So when I say order, I don't just mean order on the set of, obviously any set of an order that gets along with multiplication and addition, sort of nice ways.
Okay.
Yeah.
Peter?
So what happens when you take just, instead of pivot spaces, just real inner product spaces? Does it satisfy all of the
Yes, it does. And indeed the scalars are valued in the complex numbers in that
So
case.
valued, so...
Yes. So in fact, a little bit of the result that I've missed off here is that, in fact, if you require these things, then the scalars are either the non-negative real numbers, or the real numbers, or the complex numbers. And in the first two cases, they'll have trivial involution. If the non-negative reals or the reals will have trivial involution. If they're the complex numbers, then they'll have complex conjugation as the involution.
Do you have any models for categories with all these features other than finite dimensional Hilbert spaces?
So here I'm really only looking at I'm really focusing on the properties of the monoidal unit object. So there are lots of very similar categories. As long as you have a category that's sort of loosely based on complex numbers and for which the unit object is simple. So for example, the category of representations of any group, of any compact group, have this property because its unit object will be very similar. So there's an easy source of lots of examples.
So there are a lot of questions. I'm going to just take two more. Ross?
So you introduced this notion of dagger limit,
Right.
and it seemed in the definition you needed to have also dagger abelian structure on the home sets and also biproducts.
Oh, right, so I used this biproduct notation when I was describing these dagger limits.
Yeah.
Right, I use this biproduct notation, but really all I'm requiring is this equation here. I've just written this as a sort of way to motivate why we should want this condition. The definition of a dagger limit certainly doesn't involve biproducts at all. It just involves this. We have some limit object L, such that the limit codes satisfy that equation at the bottom.
So can you derive dagger limits from dagger biproducts?
No, but good. I should have almost planted that question. So I have a final slide. But, sorry, that's to show dagger limits. Sorry about that. So in fact, if a dagger category has a zero object and all dagger biproducts, all dagger equalizers. So dagger equalizers are sort of equalizers in the ordinary sense, but with the extra requirement that this equalizing that E is itself an isometry. And then we need this extra, slightly annoying condition that any two isomorphic objects are actually unitarily isomorphic. There's also unitary isomorphism going between them. Then you can prove that you can actually reconstruct you have all finite dagger limits. So you can't just get it from dagger biproducts. But you can get it from dagger biproducts, dagger equalizers, to zero object.
Okay. Tim, the last question.
Oh, I just wanted to ask, I mean, you're talking about physical insight. I mean, where does this fail in describing classical physics?
So I suppose the way it fails to describe classical physics straight, first of all, would be, so I don't know, let's say we forget everything we know about quantum theory and we try to do this. What would you take as your systems and processes? Maybe systems would be sort of classical configuration space, symplectic manifold or something. You could think up something plausible for your processes. You have a lot of trouble coming up with a dagger functor, something that for any process from system A to system B, you in a well-defined way get a process that goes from system B back to system A. You would have a lot of trouble. That's a sort of symmetry that classical physics tends not to have. As quantum theory